SwayamPrabha. Digital India. Educated India.
All right.
Yeah.
So my name is Balaji. So I have to qualify that I am C Balaji. C standing for Chakravarti. That's my father's name. So we also have Professor S Balaji, my colleague. So we'll also be teaching this, co-teaching this course along with me. S Balaji, are you there?
Yes, sir.
Can you just turn on the video for the benefit of the students? Then you can again come back up. Yes.
Hello.
So
Yeah.
this is Balaji and Balaji. Okay, so you got a double pronged attack. All right. So we will be. So we are colleagues in the same lab. We are sitting in the heat transfer lab. Okay. So we'll be offering this course this semester. So this is an experiment we started in the year 2019. So you're the third batch. So I don't know whether all of you are aware that such courses, to the best of our knowledge, do not exist anywhere in the world. So I think because of our interest and our work in these areas, we have put together material and then started it as an elective. It was well received. The first year itself, 100 students joined the course. Last year, 100 students have joined, and we are able to. And it's contemporary. That's why I think it appears to be contemporary. That's why so many students want to take this course. According to us, it's more like applied common sense. This course is like an applied common sense. This inverse methods in heat transfer is only an excuse. We have to put it on some domain, right? So we are putting all the techniques in the domain of a heat transfer because we are basically specializing in heat transfer. We sit in the heat transfer and thermal power laboratory in the Department of Mechanical Engineering. But if you're a discerning student, you'll be able to understand that you'll be able to figure out that these techniques are general. This can be applied in a wide variety of fields, whatever be your domain, whether it is financial engineering, geology, sociology, management science, okay, electrical engineering, mechanical engineering, whatever. All right, but we have kept it as inverse methods in heat transfer so that it doesn't make. Otherwise, it makes it too diffuse, and our examples are to be taken from other fields, and we don't have the domain competence to properly choose examples from other fields because of our work in the heat transfer and thermal sciences. So we are very comfortable with this domain. So we are able to come out with meaningful examples, and so that we can steer the course and achieve the objectives. Okay. So people who have not formally joined the course and got this invite from their friends, please write to Rajesh Akula, the TA. Okay. Rajesh Akula is here. Okay. So you will get his contact. He has been sending mails. He will send the mails for the invite. The plan is like this. The course will be offered. Okay. Before I forget, this course will be offered in D slot. So the class timing. So we'll have the lectures on Zoom. Okay. So we'll record your attendance also on Zoom. Rajesh will tell you how to do that. But this is only for just for the purpose of keeping the record. We're not going to use it against you. But if somebody has attempted all the quizzes, enzyme, this thing, whatever we are asking to do, and then most of the times he has marked his attendance, we'll give him VG grade. Other people will give G grade. Don't worry, because somebody is not having a Zoom connection doesn't mean that we will give a P grade for attendance. Don't worry about attendance. Okay, you have to learn. That's more important. And all right, so the plan is about 40 lectures. So about 30 to 32 will be, I'll be handling about 30 to 32 lectures. So about 8 to 10, Professor Balaji Srinivasan will be handling. So his portion will be mostly neural networks. Okay, so this will be intro and classical techniques. Okay, that will what, and then so finally you have to marry these two so that you will be able to tackle problems of reasonable difficulty. All right, so we'll try to keep it around 40. It won't be minus, maybe 1 or 2 extra maybe there. Okay, all right. Now Grading policy will be so all quizzes, exams. All exams and quizzes will be take home. That means it won't be take home, means we will not give infinite time. So the quiz will be set for 50 minutes and you will get another 30 minutes or 40 minutes to upload. A4 sheets, A4 sheets, you can use your notes, this thing, you can refer to whichever source you want. Generally, you're expected to refer to only the notes. So then you complete the answer paper, scan it on your mobile, make it into a PDF, and then we'll set up a link and then you will submit it. How does it work? Those people, we are doing it for the last 1 year. So many courses we have already completed. This method work. How do I prevent copying? All the question papers will be roll number specific. We'll do a lot of, we have already done a lot of thought into this. No two questions parameters will be the same. So you just cannot copy because everything will be based on your roll number, first digit, second digit, last digit, third digit, the last digit by 2 into 2, all that. So there's sufficient this thing. So no two question papers or answer papers will be alike. But there is no tension of 50 minutes, mean 51st minute you have to submit. So we'll give some reasonable cushion for you to submit. So this method works well so that you don't have to travel anywhere. This is assuming that this model will continue till the online model will continue till the end of the semester. If institute changes its policy in between, we'll take it as we go along. But I don't think up to quiz 1 there will be any change. So we'll do 2 quizzes. So 40%. So the end sum will be 60%. If there is an assignment test, we don't know. I have to discuss with Professor S. Balaji also. If there is an assignment test, then we'll make it 10%. What is the difference between assignment test and this is? It will be little more relaxed assignment test. Maybe we'll give you 1 more day to submit or something. If then if we give an assignment test, then this will become 50%. Okay. So the assignment test may or may not be roll number specific. So we just want it mostly a practice. So if this is agreeable, so which do you want? You want 2 quizzes and then some, or there is one assignment test where you can practice, you get more time. Even if you have a doubt, you want to talk to your friend, it's okay. But it is your work. You will do it and get some credit. So I think we will get to use this model. 2 quizzes, 20%, 20%. This one 10% take home assignment test. And this will be, or you can say take assignment. Okay. So this is take home. And then end semester will be 50%. There's no schedule for the quizzes as such. We will just see that. So we have that 12 o'clock class. So we can start the quiz at 12 o'clock and 12:50 you can complete. You can take time up to 1:30 to upload the papers. Okay. So we will generate roll number specific solutions and then we'll share the solutions with all of you. Then we'll also share the graded answer sheets with you. You can assess your own paper. You can come to conclusions about how many marks you have got. You would have, in your assessment, how much you would have got. If your assessment and our assessment is off by more than plus or minus 5%, then you can come back to us and crib and say there is a problem or there is a totaling mistake and then it is unfair. I should have got more marks, whatever. Okay. So marks and all that we'll take care. It will be fair, all neutral, everything. But the funda is you have to learn. Okay, you have to learn. That is more important. Learning. So this exam is after all one instrument. Okay, one instrument to measure your learning. And if there are only few students, there's no need for an exam at all. We can just have an interview. We can just have an oral exam or just talk to you and find out whether you have learned it or not. All right. So exam is not the be all and end all of everything. So this is D slot grading policy. And so the 30 lectures and 10 lectures between me and Professor S. Balaji, the plan is I will start because mine is fundamental and you don't even know what is inverse. So I will go all the way for the first 2.5 months or so. Then the last 3-4 weeks he will come. Okay, that is the plan. So quiz 1 will be mine and quiz 2 could be mine or mine and says Balaji half. End sum will be mixed. Is that okay? We might make the end sum into part A and part B, and that's what we did. For example, only last week we had the exam for this course for the last year batch, the non-graduating batch. So it has taken a year for them. So I had to have some refresher classes in between. It's a long time since I took this course. Anyway, that is done now. All right. So inverse methods in heat transfer. Heat transfer is something which you know. Heat transfer is a mode of interaction at the boundary of a system, which which is a consequence of the temperature difference. Okay, so there are in thermal engineering, in thermal sciences, the two most important interactions are heat and work. Why are we obsessed with heat and work? Because the original idea was to be able to convert heat to work, because work is considered as a superior form of interaction, because this mechanical work can be converted to electrical work, and it can be transported over long distances. For example, there is a power plant working in Ramagundam. Somebody thousands of kilometers away can enjoy that power. So mechanical energy as such has to be absorbed, has to be enjoyed or used in that place itself. Whereas if it is transported in its electrical avatar, it can travel long distances. Then you have AC transmission, DC transmission, high voltage, low this thing, all those things come under grid technology, electrical technology, and power, what is high voltage engineering and all that. So why is work so important? Because fundamentally work reduces human toil, TOIL. So work is some sort of godsend. That's why thermodynamics continues to occupy a special place. Of course, now with electric vehicle technology and solar photovoltaic cell, the heat engine route is getting bypassed. But even so, the last 200 years, 150 years or 200 years, the thermal engineering has been central to the generation of power. And so you can, from one place, you can generate thousands of megawatts, which can be transported over long distances. Okay. So when you convert heat to work, invariably there will be some losses, and even heat is not directly available in its form. So invariably it is available in the form of chemical energy of a fuel, which could be a petroleum, or it could be a gas, or it could be coal or wood or whatever. So there is a conversion from chemical energy to mechanical energy, and then from this energy, it's converted to electrical energy. So see for example, the chemical energy of the fuel is converted to heat, and the heat is absorbed by water. Water is converted to steam, and using technologies like high power nozzles, high nozzles, and so on. So you convert them into high enthalpy steam. These high enthalpy steam impinges on the blades of a turbine, and then you just get a torque, and then this is the mechanical energy, and then it is connected to a turbo generator, from where you get the electricity, 440 volts, three phase, whatever, and then it is stepped up to 25,000 volts or 11,000 volts and all that. Okay, and then it is stepped down again somewhere, and then three phase to convert to one phase, whatever you want to do. All these are electrical technology. All right. So heat transfer has been central there, because the early efforts in thermal engineering have been to convert heat to work. Okay, but there are independently, heat transfer is also very important, because any human enterprise, invariably heat is generated, and certain devices, invariably all the devices do not work at their optimal capacity beyond a certain temperature. And if beyond the optimal temperature, if a safe temperature is exceeded, they will fail. First, they'll become less reliable and they'll fail. This is true for a laptop, desktop, workstation. Even if it becomes very hot, sometimes even the mobile phone can explode. You have read stories. Okay, then the data center, the computer center has to be kept under appropriate temperature and humidity. Your auditorium, whether you're watching a movie or listening to a concert, it has to be under controlled conditions. Your airplane has to be under a particular temperature and humidity. Your air conditioned train, your air conditioned malls. So when you come to the issue of thermal comfort, because the temperature and humidity are not always desirable outside because of due to the vagaries of nature, you want to be under a constant temperature and humidity condition throughout. There are devices which are generating heat. There are many people sitting in auditorium. Apart from computers, people are also, because of metabolism, they're generating heat. So the heat transfer is fundamental. Heat transfer is there in a wide variety of applications ranging from aerospace, chemical, metallurgy. So, you name it, heat transfer is there. Heat transfer is there. So much of heat transfer and mass transfer within the body. Okay, there's a bioheat transfer. There's a lot of metabolism. High heat is generated in cancer cells, metabolism. So you want to understand how the cancer spreads, and if you want to kill the cancer, again you put laser heating or X-ray and all that. So there is some heat transfer associated issue in many walks of life. Okay, in many branches of science and engineering. So now heat transfer is something which all of you have studied either as a BTech student or MTech student. Have already studied as a part of your BTech. 6th semester or 8th semester BTech students of IIT have already done it in the 5th semester. Now we are doing something to the inverse methods of heat transfer. So there should be something called inverse heat transfer. So when you're doing an inverse heat transfer, it is not so straightforward. Therefore, there should be a method in that. And this method is not so apparent. It is not like solving ax squared plus bx plus c equal to 0 or 2x plus 4y equal to 0, 3x minus 8y equal to 4. Solve the two equations. It is not so straightforward. Therefore, inverse is something which is added on to heat transfer. So the fundamental, the core is heat transfer. In that, I want to do study an inverse of that. In that, when I study inverse of that, I need to know certain techniques and methods. Therefore, this course is titled Inverse Methods in Heat Transfer. It could be, the more general course could be Inverse Methods in Science and Engineering, then where we could open it out for all the students. Then this will be a Janta course where then we have to be very careful about what sort of problems we'll ask. Eventually, it may become like this. If the course gets popular and there's a demand from other people, other branches. Okay, so let us say the basic funda. What is the funda actually? Okay. So look at any phenomena. Look at any phenomena or activity. Okay. There are some causes and there are some effects. I have put deliberately yes within bracket because there can be one cause leading to many effects, several causes leading to the same effects, several causes leading to several effects. Normally, the way, so the analytic intelligence, if you look at analytic intelligence, we are very comfortable with having a theoretical background, theory, okay? Particularly IIT students, theory, you have a belief that everything can be solved by theory. It takes a long time for you to overcome that belief, okay? But it's good to believe that everything can be solved by theory, okay? So let's say you draw some arrows. If this is the cause, this is the effect. So we are very comfortable. Then this is analytic intelligence and all science and engineering, no problem. Okay, any branch of science engineering. Okay, there is a medium which aids the growth of bacteria or amoeba. Okay, I want to model the multiplication of amoeba or bacteria here. Okay, it becomes like this. Obviously, it can be modeled. Okay, how the multiplication rate. So the basic premise of that, the multiplication rate of amoeba will be actually proportional to the number of amoeba present at that time. Then if I know what is the number of amoeba at time t equal to 0, then I will be able to predict the number of amoeba at any point later on. Okay, this is this thing. This is in let's say this is one modeling approach. Then coming to familiar heat transfer, there is a slab, one-dimensional, steady, conduction, QV equal to 0. Then I say the left-hand side of the slab is at a temperature T1. The right-hand side of the slab is at temperature T2. Then the length of the slab is L. Thermal conductivity is K. Now, what is the challenge? Challenge. Get Q. Okay. How to do this? I want to find out what is the heat transfer across the slab. Okay. So this is the notebook. This is the slab. I put this side of the notebook 100 degrees centigrade. This place is 70 degrees centigrade. Please tell me what is the heat transfer across the slab. Sir, who cares? Sir, let it be anything. No, I cannot say like that. Because I want to design an auditorium. I want to know how much load, heat load is in the auditorium, so that I am a designer of an air conditioner for a mall or for an inox theater. In each wall, I need to know. You cannot say, I don't know. Who cares? It is an engineering problem. You have to solve that problem. What is one way of doing it? Okay, just measure it. If it is already there, I will measure it, number one. Or it is already there, it is very difficult and expensive for me to measure. So I don't want to measure, I want some theory. Okay, now the question gets tougher and tougher. Suppose you are a designer, the wall is not there. So, but I want to tell what will be the thickness of the wall, or if it is a particular thickness, what is the material, so that this is the amount of heat transfer which will take place. Or if I build it of this material with this thickness, can you turn around and tell me what is the Q? So this is a fundamental engineering question. So just measure it, it's easy to say, but often it is difficult. Therefore, can we get it from theory? So, what are the causes for this Q in this problem? The causes for the Q in this problem are there is a material with a thermal conductivity, there is a conduction which is taking place, and there are two boundaries at T1 and T2. The two temperatures are T1 and T2. Now, if you solve it, now the governing equation will become, we'll see it in a, already you know this. So d by dx of k dt by dx equal to 0. Okay, if k is a constant, if k is a constant, d square t by dx square equal to 0. Integrating twice, dt by dx equal to a. Integrating again, c equal to ax plus b. So this is the solution to the problem. Okay. No, sir. Somebody says, no, sir, that is not the solution to the problem, sir. What is the question? Sir, I want to know what the Q is. I want to know what the Q is. Okay. Now I will say dt by dx into Ka equal to Q. Okay. If I know the T, I can get dt by dx, and I can find out the K is the thermal conductivity. From this, I can get the Q. Okay. Q is nothing but heat flux, is the heat transfer rate by area. So this A, so x equal to 0, T equal to T1, x equal to L, T equal to T2. There's two constants and two unknowns, A and B can be found out. Therefore, it is a revelation that for a constant thermal conductivity, no heat generation, steady state conduction in the problem, the temperature distribution is linear. So you understood something more, which you may not have figured out if you measure. So T equal to AX plus B. Then there is something called Fourier's law, which can be applied from there, and then you'll get it. Actually, this equation itself comes from Fourier's law. Let's not get into that now. So once you differentiate it, you will get the Q. So there is a set of causes. There is a slab with thickness L, which has a thermal conductivity K with all the conditions. There are two boundary conditions. So now the effect will be, the temperature will be like this. You can predict. So this is modeling. This is analysis. This is what we teach semester after semester in all branches of science and engineering. Given this problem, this is the solution. Given this problem, this is the solution. We call it as the direct. So this, in the parlance of inverse heat transfer, this is called the forward model or direct problem. There is no dilemma for you. Theory is there. How to prove that this is correct? So if you actually measure the temperature, it will be linear. After all, this one Fourier obtained by doing experiment. He found out that whenever he conducted experiments on conduction in rods, he found out that if the rod is longer, the resistance to heat transfer is more. If the area of cross section is more, the heat transfer is more. If it is a metal, somehow it conducts better. So he classified that, he figured out there is a property which is inherent in the material, which will decide whether it will conduct more or conduct less. Therefore, materials can be classified based on something, some animal. That animal is called thermal conductivity. You define a new property called thermal conductivity, but the material does not know that it has a thermal conductivity, because human being has invented the thermal conductivity so that he can understand and conquer. The material will behave according to its own dharma. It is not only thermal conductivity, the material has other properties. It may be a solid, it may be a semi-solid, okay, it may have a different density, it may have a specific heat. So depending on your purpose, you are characterizing. So you are studying it only from the viewpoint of heat transfer. So that you have said that this is a conducting material does not exhaust all of its attributes. It exhausts only those of the attributes which are central to your understanding of that particular problem which you have in mind. If you are a stress analyst, you will not even worry about this. You will worry about something. What are the stresses? Therefore, it's like this blind element trying to several blind men trying to find out what is the shape of an elephant and so on. Okay, please understand the limitations of science. Okay, from the point of view of a thermal engineer, this much of characterization is enough, because the goal, I set out with the goal of finding out the heat transfer. So I have a construct. What is that construct? I have a construct called the Fourier's law, which somebody, my forefather, he already did the experiment, and he gave an empirical law. Then I used thermodynamics and put the Fourier's law into it, and I got a governing equation. This is called the steady state conduction equation. And my friends, okay, my forefathers, Newton and gang, they said there's something called calculus. There's a differential equation. I can solve it and integrate it, and then the whole discipline of mathematics. Okay, so everybody is a partner in this crime. What is this crime? Trying to find out what is happening in this lab. Okay, they're all partners in the crime. Scientists, Newton, Fourier, all that. Finally, we have all these partners have finally figured out that there is a linear temperature distribution. From this, you can get the K. All right, but the problem gets tricky when I actually go to the lab, or somebody is trying to figure out, somebody has come with an unknown material, or you want to do reverse engineering. Let's say you get some material from some country or something, and it has some special properties. For example, you're interested in insulation, and this material seems to have some magic properties of very low thermal conductivity or very low this thing. Therefore, you want to characterize the material. So you're doing some experiment. Now you put some thermocouples. Okay. Thermocouples TC 1, 2, up to 5. So I am getting temperature T1 to T5. Now, whenever you do a measurement, it has got an error. Okay. All these 5 measurements have an error, but I have done my measurement science. I know the fundas of the measurement so that I will tell you whether the temperature is 45 degrees plus or minus 0.1, 45 degrees plus or minus 0.2. I can turn around and tell you what that is. Now, if there are 5 temperatures given, you please tell me what the value of thermal conductivity is. What is the thermal conductivity of the medium? So, this is the inverse problem. So, what is the inverse problem? The effect is the temperature is effects are known or measured. From here I have to get a cos. So effects are T1 blah 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 to T5. The cos is thermal conductivity. Then says, sir, no problem, sir. I'm a heat transfer genius. Very good. You're a heat transfer genius. What is this? Elementary problem, sir. Steady state, one dimensional. No problem. No problem. I'll do it in a jiffy. Yeah. Let's see how you do it. Just now you taught us. What did I teach? T equal to AX plus B. So if you take dET by dx, okay? If you take dT by dx and if you take dt by dx, if you know this t equal to ax plus b, you can get dt by dx. From this, from q, you can get the k or whatever, sir. You can solve the problem. Okay, you can solve the problem. Okay, that is okay. So you are saying that you can solve the problem. Now the question now is, it is a linear temperature distribution. A straight line can pass only through 2 points. I have 5 temperatures. 5 is just an excuse, man. I can get 25 temperatures. So in this case, let's say that I have 5 temperatures. I will have 5 C2 combinations. I can take the temperature T1 and T3 and get a value of thermal conductivity. I can get temperature T2 and T4 and get another thermal conductivity. Which thermal conductivity is right? Now comes the question of 5 temperatures seem to be too much for getting the thermal conductivity, because if I give you only 2 temperatures, you will go back to your steady proper heat transfer and say T equal to AX plus B. Sir, you gave me T1 and T2, I'll find it. But life is not like that. We have more measurements than what is possible. Then why are you making more measurements? Because no measurement is perfect. The more the data, it is better for me. Nobody worries about whether it satisfies equation, because equation is there only in the mind. Equation and calculus are only to help us. It can't take us beyond a certain stage. Okay, so stop that idea of it should satisfy equations. And equation is basically for you to understand. I want to engineer a material which will have this thermal, whose material I want to characterize this material, which seems to be giving a super duper performance. Therefore, this is more important whether my differential equation is satisfied or not. That is like a low level, because you are stuck to your mathematics. Even with your mathematics, this material is a dharma, it will behave, it will conduct or not conduct. This heat transfer equation solution is basically your inability to understand it fully. So you're understanding it through the route of mathematics. Let's get it there. Okay. Now, if there are 5 temperatures, I'm in trouble. If there are 20 temperatures, I'm even more in trouble. Now, with whatever I've taught you, you cannot solve this problem. You might have got an S grade in heat transfer. You cannot solve this problem, because you don't know the techniques as to solve this inverse problem. So welcome to inverse heat transfer. Now you know why this course is called inverse methods in heat transfer. This is only one case. For example, if somebody takes a CT scan and then the doctor is figuring out there is a cancer, how is he figuring out? It is because of the absorption by the tissues. So there is a radiation problem. So the CT scan gives a 3-dimensional construction of various 2-dimensional views. So how to separate the normal tissue from the cancerous tissue? All these are part of some inverse. This inverse is going on. It's going on in all branches of science and engineering. When you go to a doctor and he keeps a thermometer in your mouth and there is a fever is a bad word now. From COVID to cancer, it could mean anything. So doctor is given a set of effects. From that, he has to find the cause. It is not so easy, because many diseases can cause fever. He has to diagnose properly. So he will ask you other things. Is your stomach paining? Are you having nausea? Are you having vomiting? Are you having a skin rash? Did you eat something, or did some insect bite you? Okay, or how long is it going on? So, and then you will ask some tests. Then you will try some crocin for some days. It doesn't work, a blood test. Then it will go to a scan. So he is using more and more data to reduce the uncertainty associated with this algorithm. So a doctor, for example, is all the time dealing with an inverse problem. All the patients, their GP, if you go to the IIT hospital, most of the time it's cold cough, fever, stomach ache. So it is, but there could be many diseases. And for everything, the medicine is not the same. The treatment may be different. Diagnosis also could be very tricky. Therefore, the world is flooded with inverse problems. Inverse problems are a lot harder to solve because several uh, so several causes could lead to the same effect, or that effect could be caused by several causes, just like several diseases can lead to the same fever. Simultaneously, more than one infection could be there in your body. Is it okay? So we don't know. So therefore, just like a physician diagnosing a disease, there are many applications in science and engineering where you make a measurement, you even have a model, but you don't know how to combine the model and measurements because you have a overdetermined system, or you've got too much data to deal with, and there are other techniques. So you need to know statistical techniques, how do you statistically estimate which is the best thermal conductivity. Therefore, some technique. Apart from this, do you have some beliefs? If you have a belief that it is a good thermal insulator, it's a high thermal conductivity material. So I can guess something. If you can guess, can you quantify your guess and put it into a model? So this is another technique. This is called the Bayesian method. Or is there a lot of data available? Can you put it into something called a neural network, which can replace the d squared t by dx squared equal to 0? So all these are part of the game. Okay, so welcome to this whole world of inverse, where this inverse methods in heat transfer is only, as I keep reiterating, it's only an excuse to get you exposed to this subject because you've all studied heat transfer last year or the year before. All these ideas are fresh in your memory. You have the heat transfer notes with you. You can, whenever there is a forward model, you have a doubt, refer to the heat transfer notes. Proceed forward. Let's go to the inverse. Once this, so this will bring in the ideas of data science, data analytics, artificial machine learning, and all that. So with these techniques, wherever you are, you can go even to financial engineering. You can go even to a B school. You can go to a PMS or PhD in operations research, or you can go to a banking or whatever. Whatever principles we teach, a few of these, if you remember, it is our belief that will stand you, all these will stand you in good stead in the next 30 years, because you may be, more often than not, life itself will present you with a lot of inverse problems. Many times you're always investigating the cause. The effect presents yourself. Why am I sad today? Why is it like this? Why is my mood not good today? Why am I not doing well? You're always investigating. Whenever you're investigating, you're invariably dealing with an inverse problem. Please be, please, mm, uh, please take cognizance of that. That whenever you're deeply contemplating of this thing, you are actually going from the effect to the cause. So, as a human being, it is our inherent nature to investigate deep into phenomena and events, even in our life, and whatever is internal and whatever is external. When you're investigating and probing deeply, you're invariably investigating a inverse problem. Okay, I would request Professor S. Balaji to share a few words on.
So I'll just make some brief comments on what Professor Balaji has said with respect to, just so that you have some, of course, I'll discuss this in detail later on the course. But you see, Professor Balaji just gave the example of a simple slab, and you are taking thermocouple measurements at, let's say, 5 points. And the key there to find out, as you will see when the course proceeds, to find out the heat transfer or the thermal conductivity is to do some kind of fit. Okay? But we will assume that it's a linear fit. And how do we know it's a linear fit? You saw the solution. You started with the differential equation. You started with d dx of k dt by dx is equal to 0. And then we got a linear equation t equal to ax plus b, and then we solved it. Now imagine a more complex situation. So let's say we, instead of just taking a one-dimensional example, you have a two-dimensional or a three-dimensional example where you don't quite know what the solution is. Or we can even add other things like varying thermal conductivity, etc., in the middle of the slab. Then you could add other things like porous media. So when you add complexities to the problem, we actually do not know the analytical solution. So in such cases, what can you do? Okay, so in such cases is when we start using things like neural networks. What are neural networks? Neural networks, even though people will discuss from one side of the machine learning side, people will talk about the structure of the brain, etc. The approach we will be taking in this course is neural networks work as a function fit. Okay? So when you don't know quite what function to fit, neural networks are a very good idea. When you have massive data, okay, when you have massive data, neural networks often work very, very well, because you have to somehow substitute for the lack of knowledge of physics. Suppose you don't know physics at all, neural networks are a good idea. We will also discuss towards the end of the course something called physics informed neural networks, which is they mix the idea of having some data and also knowing the governing equations. In such cases, how can we solve inverse problems? Some of the students in the lab, Professor Balaji students, my students, have also worked in physics informed neural networks, and we are finding very good results here. This is a field that has come up only over the last couple of years. So we hope to introduce you to both neural networks in a general sense. As Professor Balaji said, general inverse methods are there in all of science and engineering. We'll be particularly using the context of heat transfer, but this is a tremendously useful field for you elsewhere also. So in case you have done a machine learning course, still we hope that you will learn the inverse part from this course, and we hope that something interesting will come out, especially physics informed neural networks. So I'll be taking 8 to 10 lectures towards the end, and you will see that the whole course will gel together very nicely after you have seen all the techniques that Professor Balaji has discussed. So we will see this towards the end of the course.